Hey guys, welcome back. We're here with day 3. We're going to look at a couple of things here quickly. We're going to look at limits at infinity, and we're going to look at the squeeze theorem as well today. Let's start talking about limits at infinity. Let's go back to something we know. When you guys were in pre-calculus, you worked with rational functions, and one of the things that you analyzed, or even before pre-calc, you analyzed the extremes, right? Let's just talk a little bit about extremes. If you had a graph that looked like this, one of the things you were asked about was what's happening at the extremes. As x gets really big or as x gets really small, what's happening out there? And one of the things we talked about, a specific type of extreme, is a horizontal asymptote. A horizontal asymptote is when when a graph flattens out and starts approaching a y value, and it maybe never reaches it out there, or it never reaches it out there, but it keeps getting closer and closer and closer. In this graph I sketched here, we see two different horizontal asymptotes. We see a horizontal asymptote at y equals 4. And we see a horizontal asymptote down here at y equals -3. Those should be things that we're used to from previous classes. We're just going to talk about horizontal asymptotes in terms of limits. What does this mean in terms of limits? Well, not only can we do the limit as x goes to 3 or the limit as x goes to -5, we can also look at limits as x goes to infinity or as x goes to positive infinity. And we need to consider both, right? So if we wanted to talk about this particular graph I drew here for you, this rough sketch, if I want to talk about this horizontal asymptote over here on the right, as this graph keeps moving more and more to the right, what x value are we approaching? Well, to go far enough, we're approaching positive infinity. You can say in this graph right here, right, if this is the graph of f of x, you can say the limit as x goes to infinity of f of x would equal what number? Well, as x gets infinitely large, what y value do we get closer and closer to? Well, we keep getting closer and closer to a y value of 4. Again, the idea of horizontal asymptotes is not new to you, but the idea of expressing it as a limit as x goes to infinity is new. Okay, but it should kind of seamlessly go in there. It makes sense. The x value we're approaching is infinity. The y value that we're approaching as x gets infinitely large is a y value of 4. Think to yourself, how would you write a limit expression for that the one over here, the horizontal asymptote that's going to the left? Well, instead of saying x go to infinity, as we go to the left, x keeps getting more and more negative. So we can say for this one, limit x goes to negative infinity of f of x. Well, that equals a value of -3. Okay. What's important to understand is horizontal asymptotes can occur as we approach infinity or negative infinity, and we need to consider both. So a couple of questions on the exam may ask you, multiple choice especially, find the horizontal asymptotes of this function. What they want you to do is they want you to find the limit as x goes to infinity, and they want you to find the limit as x goes to negative infinity. Finding these when you have a graph is pretty simple, but it can be a little bit more challenging when we just are dealing with a function. So let's talk about how that works. Again, some of this you're going to be used to, some of it you may not. First function I want to look at is f of x equals 1 over x. Okay? My questions for you is, what is the limit as x goes to infinity of f of x? And what is the limit as x goes to negative infinity of f of x? To answer these questions, you may already know the answer to these questions. Okay? Well, but I want you just to think about what's happening. What happens if I plug in, we'll do the limit as x goes to infinity first. What happens if I plug in a big number like 100? Well, what I get is 1 divided by 100. If we think about that as a decimal, that's 0.01, right? 1/100th. If I plug in a bigger number like 1,000, I get 1/1000th, 0.001. If I plug in a million, I get 0.000, however many zeros there are, 1. As x keeps getting bigger and bigger, when I take a number like 1, or really any number, 5, 6, 7, any number but 0, if I take a number and divide by a really huge number, I keep getting numbers closer and closer and closer to what numerical value? Well, that would be 0. So we know, since the limit as x goes to infinity of f of x equals 0 here, we know that a horizontal asymptote of f of x is y equals 0. Now let's also check negative infinity. Sometimes we'll get the same answer, sometimes we'll get a different answer. And it's important to always check both. What happens now if I plug in a really, really big negative number? Well, if I plug in negative 100, I'm going to get negative 0.01. If I plug in negative 1,000, I'm going to get negative 0.001. If I plug in negative 1 billion, I'm going to get negative 0.0000, right? So I'm going to get these numbers, and I keep getting closer and closer. Even though I'm on the negative side this time, my numbers are still really, really, really close to 0. So I get the same answer of 0. If we know what the graph of 1 over x looks like, sometimes that can help us think about this. This is what the graph of 1 over x looks like. And we can see that we have a horizontal asymptote of 0 out here, as well as that same horizontal asymptote of 0 on the other side. All right, let's take a look at another function. These base functions will kind of help us when we get to more complex stuff. Let's look at f of x equals e to the x. We're used to exponential. We should be hopefully used to exponential functions. We know e is a constant, right? Kind of like pi. It's a number, 2.7 something. Okay, and that is now being raised to the x power. So again, I want you to think about what's happening as we do the limit as x goes to infinity of f of x. And I want you to think about the limit as x goes to negative infinity of f of x. Okay. Again, don't be thrown off by the fact that e is kind of a weird number. Just think of it as like 3, right? If we take 3 to the power of 2, we get 9. If we get 3 to the power of 3, we get 27. 3 to the 4th is 81. We see that we keep getting bigger and bigger and bigger numbers over and over again. If I take that number e and I raise it to an infinitely big exponent, it's going to create a really, really huge number, right? So it's going to keep getting bigger. No matter, right, the bigger I make x, the bigger I make my y value. So I don't get a horizontal asymptote from this side. I just get that this equals infinity, positive infinity. But it's a little more interesting when we look at the limit of x goes to negative infinity. What I want you to think about is, how do you solve negative exponents, right? Let's think about e to the negative 5 real quick. If I ask you to evaluate e to the negative 5, well, we can rewrite negative exponents in the denominator as a positive exponent. This is like 1 over e to the 5th. So when I think about e to the negative infinity, I think about that as a problem. I'm going to have 1 over e to the infinity. Well, I already know that e to the infinity makes infinity. Okay? So what happens then when I have that in the denominator? Right? This thing is getting huge. But we know from our previous example, if we take a number like 1 and divide by a huge number, 1 divided by a huge number is going to approach 0. Our limit of x goes to negative infinity is in fact 0. If we think about the graph of e to the x, a very helpful graph to know for this course, the graph of e to the x looks like this. So again, we see this horizontal asymptote. Like this right here, y equals 0 is our horizontal asymptote. We don't get a horizontal asymptote from this side, from the right side of the graph. Okay. Good. The next thing I want to talk about is, what if we have rational functions? Okay, and this should be something we kind of already know. But let's take a look at it anyway. Okay. So here's a rational function. And if you remember from pre-calculus, right, you're asked questions like, what kind of extremes do we have here? Okay. Well, what happens is, if we plug in an infinitely big number, the top is getting infinitely big, right? If I take infinity squared, right? If I take a billion squared plus 5 times a billion minus 2, that's a really big number. But so is a billion cubed plus 2 times a billion squared plus 1, right? Both the top and the bottom are getting really, really, really big, okay? What I want you to understand here is that they're not getting big at the same rate, okay? Because that denominator has an x cubed, what I like to do is look for the most powerful exponent. The most powerful exponent in the numerator is the power 2. The biggest one in the bottom is the power 3. Okay? The one at the bottom is bigger here. Even though I have a really big, right, when I plug in a number like infinity, even though I have a really big number on top, I have a much, much, much bigger number on the bottom. So in a sense, that top number isn't so huge anymore. I have a number divided by a huge number, which is always going to give us 0. Okay. If I plug in negative infinity, going to be a really huge negative number on the bottom, because x cubed, right, when you cube a negative number, it stays negative. The top is going to be really huge, but not as big, positive. And still, I have the bottom being more powerful. So whether it's a going towards infinity or negative infinity, I'm still getting 0 either way. Try plugging that into your graphing calculator and see that there are a horizontal asymptote there is a horizontal asymptote at 0, and it occurs going both directions. Okay, what about if the top is more powerful?
So when I want you to know bottom more powerful, our limit as x goes to a and f of x is going to equal 0. That's going to be true anytime the bottom is more powerful. If the top is more powerful, f of x equals 3x to the 6th plus 5x cubed over 2x to the 5th plus 4x to the 4th. When I look at this equation now, I see that the top is more powerful than the bottom. Okay? So now I see the top has the bigger power. So let's think about our limits as x goes to plus or minus infinity. So if I plug in a really big positive number, both the top and bottom will be really big positive numbers. But that top is growing at a bigger rate. Okay, since it's a huge positive divided by a not as huge positive, I'm going to get positive infinity coming out of this. I do the same analysis with a negative really big number, because again, I'm really only focusing right here on my most powerful ones. A negative number to the 6th power will make a really big positive. A negative number to an odd power in the bottom will make a not big, but not as big negative number. So it's going to go to infinity, but because the top is positive and the bottom overall will be negative, right? We'll end up going to negative infinity. Let's talk now about what happens if there's the same power top and bottom. When I analyze the powers here, I see I have the top and the bottom, both of them have the same high power of 3. So when I take a look at this, okay, I notice that these two match. As a result, this will be our answer. The limit as x goes to infinity of f of x is going to equal 4/3. All right, I have to end because this classroom is being used. So this video will be in 2 parts. So I'll talk to you guys later. Bye. Sorry. Oh, no, for some reason my computer's like frozen. I am not. You have to see how the AV works in this room. Oh, yeah. It works pretty good.